Okay, so to pick up part 2 here of Note 7-3, we'll pick up with example 3. And really what we've seen so far is how to calculate the rotational kinetic energy, which again is 1/2 moment of inertia times omega squared, the angular velocity squared. And then the last thing we left off in the last part of this video was really talking about the conservation of total mechanical energy as long as there's no outside force. And this is a good example to illustrate kind of the differences with how we can work this problem now that we're more aware of kind of the center of mass and the moment of inertia. So anyway, we've got a 1 meter long 200-gram rod that's hinged at one end and connected to the wall. It's held out horizontally and then released. What is the speed of the tip of the rod as it hits the wall? Okay, so let's just first and foremost make sure we're pretty comfortable with this situation. So you've got the rod, which is originally horizontal, and then it's hinged at one end here, right? So it's held out, it's said like that, and it's being hinged at one end. So then it's released, and as it's released, obviously that rod then is going to swing downward, right? So starting here and then swinging downward, that rod is going to eventually be vertical. And they're asking us, what is the speed of the tip down here? So how fast is this moving as it hits the wall, right? That's what they're asking us to find. So the first thing here to get us going, right, to find the velocity is going to be just a consideration of energies. And again, I know it's not always the easiest approach to take, but it is the easiest one to calculate if we can get our mindsets focusing on energies. So the idea of this question is we've got the rod, and because it's a uniform rod, and they didn't tell us otherwise, so we'll assume it's a uniform rod, then the center of mass is going to be right in the middle, right, of that rod. So I know that the 0.200 kilograms is going to act as though it's acting from the center of that rod. So then as this rod pivots downward, right, the center of mass is now down here. I can find the change in height from the center of mass. And the key there is, as the center of mass falls down, I'm losing potential energy, right? As this falls down here, I'm losing some potential energy. And where does that potential energy go? Well, again, if there's no outside force acting, which we're not told there's any friction or anything like that, then we're assuming that any potential energy we lose has to go to some other form of energy, right? So in this case, since the rod is not sliding up or down, it's not translating, right? It's not sliding up, sliding down, sliding left or right. It's rotating. So the only form of kinetic energy that it's going to gain is rotational kinetic energy, right? So it's not gaining linear kinetic energy. It's just gaining rotational kinetic energy in terms of the entire object. Now, obviously, each point down here is going to gain kinetic energy in one direction, but as a whole, this object is only rotating. It is not sliding. It is not moving up or down, right? So again, this just becomes focusing on my change in potential energy. So mg times h equals 1/2 the moment of inertia of the rod, and then omega squared, right? So we know the mass. We know the mass is 0.2. We know, obviously, as always, the acceleration of gravity is 9.8 unless it tells us otherwise. And then the change in height here would just be half of the 1 meter length of the rod, right? So it is important we realize that the center of mass only falls down half of the length. The mass does not fall the full length of the rod, right? So the center of mass is just going to that position, which means this height here is just half the length of the rod, so 0.5, right? So I've got that, and then on the other side of the equation I have 1/2 my moment of inertia times omega squared. So once again, if I want to find the angular velocity, the key becomes, can I find the moment of inertia for this rod? Well, the moment of inertia for this rod, if it's pivoted at one end, the moment of inertia for a uniform beam is 1/3 mass times length squared. So in this case, it's 1/3, sorry, not 1/2, times the mass, so 0.2, times the length, which is, right, 1 squared. So I can pretty easily, hopefully, calculate my moment of inertia, right? So my moment of inertia ends up coming from this, and then just plug that back into that equation up there, right? So at this point, I'm just going to plug it all in together, and then obviously you guys can calculate it from there. So here's my change in potential energy. That's all converting to the change in rotational kinetic energy, right, which is represented by 1/2 the moment of inertia times omega squared, and then it's just algebra, just a little bit of calculation here, right? You should hopefully get about 5.42 radians per second once we've square rooted that. So that's my final answer, right? So 5.42 radians per second. I do have to be careful there though, because that's the final angular velocity. Okay, so I guess that's not actually my final answer yet, right? that is my final angular velocity, but then it did ask me for how fast is the tip of the rod moving, right, as it hits the wall. So it is both my final angular velocity and my final linear velocity in this particular case, because if I want to find the linear velocity of a point down here, to find the linear velocity, we know the linear velocity is related to the radius times the angular velocity, and I know that the radius all the way down to the tip of the rod would be the full length of the rod, which in this case is 1. So it's going to be 1 times 5.42, and we can obviously use our 1 rule here, right, and get that my linear velocity is also 5.42 meters per second. But anyway, so we do have our linear velocity, which happens to be the same as our angular velocity, and hopefully this problem wasn't too bad to set up. It is a very good question, though, for kind of identifying what we can do with the change in potential energy of the center of mass and relating it to the gained potential energy, or the, gained kinetic energy for our angular motion. Okay, so then that leads us nicely into kind of the segue again of torque and force, and we're going to make a comparison between the two. So if there's a net torque, then there is an angular acceleration, right? Just like we saw if there's a net force. This is going all the way back to first semester in last year, obviously. But if there's a net force, then we know that if there's a mass, then there is an acceleration. So if there's a net force, there has to be an acceleration as well. The exact same parallel is true for rotational motion. If there is a net torque and there is a moment of inertia, then there is an angular acceleration, right? So look at this equation, and I do want to make sure everybody's comfortable with the fact that this equation here is the exact same thing, right, in terms of the angular equivalence. Force is equivalent to torque for angular motion. The moment of inertia is equivalent to mass for angular motion, and then obviously my angular acceleration is equivalent to the linear acceleration when we talk angular motion. And then of course, even though you're not in class, that does not mean you get to escape my terrible puns here, right? So this opens the door both figuratively and literally, right? Because torque is what caused doors to open. But anyway, it's a more complex dynamic and equilibrium problems. So dynamic problems are those where there is a net torque. Equilibrium problems would be those where there is not a net torque, right? What equilibrium implies that the net force is either 0, or if we're talking angular equilibrium, the net torque is 0. Right? Dynamics imply that the forces and torques are not 0. But anyway, just to recap, and then we'll see some more examples involving these type of relationships as well. But just something to make sure you're all pretty comfortable. Okay, so example 4 is kind of a fun one here to get play with the new relationship we just looked at. So far out in space, and the significance of that is if it's far out in space, we're going to assume that there aren't any other significant forces acting on these two rockets. So we've got a 100,000 and a 200,000 kilogram rocket that are docked at opposite ends of a motionless 90-meter long connecting tunnel. So we have this connecting tunnel here, and then at opposite ends we have these two rockets that have been docked at either end, right? So I've got a rocket there, and I've got a rocket here. So they're rockets, of course. They have to have some type of little wings down there to let us know they're rockets. But anyway, this is what we're looking at, right? So the tunnel is rigid and its mass is much less than either rocket. So that's basically saying we're not worried about the mass of the beam, which is nice. It's going to simplify that a little bit for us. The rockets start their engine simultaneously, generating 5,000 newtons of thrust in opposite directions. So what that's saying is one is going, right, one's thrusting this way, so it's going to move downward. The other one's thrusting this way, so it's going to move upward. So they move in opposite linear directions, but they're actually both going to cause the same rotation, right? If I look at the way that I've drawn this diagram, they're both going to cause this system to then rotate in the clockwise direction. What is the structure's angular velocity after 30 seconds? So we're looking for our angular velocity, we're looking for our omega after 30 seconds. So the key to this question becomes, right, we know that the force acting is 50,000 newtons. So we know each of those is applying 50,000 newtons of force in either direction. But because they're going opposite directions, the net force is going to be 0. So this docking station in this rocket system, it's not going to move up, it's not going to move down, right? The only thing it's going to do is rotate. So if I want to find its rotational motion, if I want to find out its angular velocity or acceleration or anything like that, instead of forces, I really need to be thinking torques. Well, what information do I need to find the net torque? And we have to be careful here, because at first you might be thinking, well, the net torque is just going to be 0. Or you might be thinking, well, the net torque is just going to be if this is the center, right, the net torque is going to be caused from half the radius times that torque plus half the the radius times that torque plus the radius over here times that torque. Not quite that simple, because it's not going to pivot about the geometric center, right? It's going to pivot about the center of mass. So the first thing we actually have to do for this system is we have to find the center of mass. And so if one of these rockets is 100,000 kilograms and the other rocket is 200,000 kilograms, right, and the distance between them is 90, I believe it was, right, 90 meters, I need to find the center of mass. And so the way that I find the center of mass, I take position 1 times mass 1 plus position 2 times mass 2 divided by the total mass of the system. So I'm going to define this as position 1 being 0. So I'm going to say 0 times my 100,000 kilogram rocket plus 90 times my 200,000 kilogram rocket, right? Because the other rocket would be the full distance away, so the full 90 meters, divided by the total mass here of 300,000 kilograms. And I can find my center of mass, right? And when I do that, so obviously when I calculate this number, I get 1.8 million, and then divided by 300,000, so I get 60. Right, I get 60, which tells me then that the center of mass is 60 meters away from the smaller rocket, and then obviously 30 meters away from the heavier rocket, right? And that becomes the key, because as soon as I find that, now I can find my net force, right? So now if I look at my net torque instead of force, right? So if I look at my net torque, the net torque is going to be the torque of the first one plus the torque of the second one. Well, torque is just force times the radius, right? So the force on that first one is 50,000 newtons, and then the radius of that first one we now know is 60, plus the force of the second one times the radius of the second one. And notice I am adding these two together because, once again, they are both causing it to rotate the same way, right? So my forces are both 50,000 newtons. One of my radius is 60, the other one is 30. So I can just use my 50,000 rule here to calculate the net torque, and I get my net torque is 4,500,000 newtons, or newton meters, excuse me. So that's my net torque. So now that I know my net torque, the question becomes, okay, how does that help us, right? We use the center of mass, we found our net torque, what can we do with that? Well, using the relationship we just looked at on the last page, the net torque equals the moment of inertia times the angular acceleration. If I could find the angular acceleration, and I know that the system starts at rest and it goes for a period of 30 seconds, so if I could find the angular acceleration, then finding the final velocity, which is what we're looking for, would be pretty easy, right? Just using a little bit of kinematics. So my goal now is to find the angular acceleration by first finding the moment of inertia. Well, once again, for finding this system's moment of inertia, it's very important that we found that center of mass. Right, the moment of inertia of this system is going to be the moment of inertia of that first rocket plus the moment of inertia of the second rocket. So it's going to be m1 r1 squared plus m2 r2 squared. So once again, very, very important that we went ahead and identified, which we did, the radius that they are from the center of mass, right, from the point at which we're going to be pivoting. Right? So we've got a 100,000 kilogram rocket, which is pivoted 60 meters squared away, and then a 200,000 kilogram rocket, which is pivoted 30 meters away, right, from the axis of rotation. So I just need to add those up to find my total moment for the system. That ends up being about 5.4 times 10 to the 8th kilograms times meter squared. So now that I have my total moment of inertia and my total torque, right, I just bring this all together. So my net torque equals the moment of inertia times alpha. I just said my net torque was 4,500,000, so 4.5 times 10 to the 6th if you prefer. My net moment of inertia here, 5.4 times 10 to the 8th, and that allows me to solve for my angular acceleration, right? So then just solving this for the angular acceleration, just plugging in, we get the angular acceleration to be about 0.0083 radians per second squared, right? And now that I have my angular acceleration, finding the final velocity is as easy as using kinematics, right? So wrapping up the second part of the video here, we're just going to finish this problem out, and then I'll finish the rest of these notes in part 3. But my final angular velocity is going to equal the initial angular velocity of 0, they were at rest, times my angular acceleration times the time of 30 seconds, and we should get that velocity to be about 0.25 radians per second. So the angular velocity after 30 seconds is about 0.25 radians per second. Very complex problem, but a good one to make sure you're comfortable.